Actually, one second. Let's get our recording started. Okay. Hi, I'm Matthew Malunik. I'm the programming team captain on 2539. And today we are going through our day 5 of our programming workshop for the 2024 off season. Today is day 5. It is logging and simulation. So we're gonna see what that's all about. This is day 5. Not right one. There we go. Already kind of went over that, but day 5 we're going over simulation. So very close to being fully through our 6-day thing. What is simulation? Basically, simulation is just a way to kind of run your robot code without actually having a robot. It's very useful for testing your code without being able to access your robot, right? It's kind of a way of like measuring your code without actually using a robot and risking breaking stuff. And also, maybe you don't always have access to the robot, right? There's only one robot. There could be a lot of programmers, right? And you want to be able to simulate your code on multiple different computers simultaneously without having access to that robot, or maybe Mechanical is doing something with it. Simulation comes a lot in handy there. So simulation-wise, simulation, WPI Lib has a built-in way of simulating code where it will run on the computer without actually running on the robot, but you do need to do some extra work to get there. So something that's technically not necessary for making simulation run, but is basically necessary if you want to actually get any information out of it, is logging and or telemetry. So logging is basically, just to distinguish these two words, logging is when you're running your robot code, right, either on a real robot or in simulation, you are recording current values, like maybe the temperature of your motors, the speeds, the position the robot is on the field, and you're recording those to a file that is permanent and gets saved, right? So that's logging. It creates a log file. Now, telemetry is more streaming information from the robot to usually the computer that is controlling it, or maybe some other device. But basically, it's like telecommunications, but for your robot, and it's kind of live streaming that data. So it's easy to get the terms mixed up. Usually you'll do both of them at the same time, but theoretically you could have your robot log data without any telemetry, in which case the only way you'd be able to see what the robot was doing is by like connecting to it and downloading the file after the match. And you could do telemetry without any logging, in which case after the match is done, you'd have no information, but while it's going, you could see like what the current temperature is. Usually it makes sense to do these in combination. So yeah, it records information out of the robot. Usually it includes time information if you're logging, so you can see like at what time was the temperature of this. And it's very, very good for debugging what is wrong with your code, because it kind of gives you a little window to look into what is the robot thinking, right? What is this variable at this time? What's actually happening inside the robot versus what do you see on the actual field? For example, if you're like trying to work with estimating pose, for example, or estimating speed, or working on autos, being able to see where the robot thinks its position is and being able to look at the field and be like, it thinks it's here, but it's actually halfway across the field over here. That can give you some insight into what's going wrong with your code. Now, simulating components, that's kind of the second half of stuff that's necessary for simulation. Basically, you need to trick the robot into thinking that it's running with real motors that are actually reacting to the inputs and moving the robot in the real world, as opposed to just kind of taking whatever speed you're taking in and just returning it as a fake motor. So it can be really complicated. You can do like physics simulations on everything if you want a really accurate simulation, or you can just go with a very, very basic simulation. That's what we're going to be doing today, the very basic option. But both of them give you an opportunity to kind of see how your robot still acts in simulation. And usually this is done to the subsystem. Usually this can be done on the like subsystem to motor level. So you might have each individual motor simulated or like an entire simulated subsystem. There's multiple options for this. You can do a lot of different things with simulation. Today we'll just be going over kind of one main way of doing this. So for logging and telemetry, there are a lot of options available. network tables is kind of the built-in way of doing telemetry. That'll easily communicate, maybe not easily, but it'll allow you to communicate information with your driver station and other devices on your RoboRio, or I guess your RoboRadios network. It's kind of complicated to use, and it's harder to send more complicated data structures over other than just like simple numbers, strings, booleans, lists. And then there's also the data log manager, which is used for logging all that data with timestamps. And these are two separate things that you kind of need to set up together, but separately if you actually want a good logging / telemetry solution. This technically can do all you need, but it's very complicated, and there's much easier solutions. Advantage Kit is I'm not going to say logging library, I'm going to say entire framework, basically, made by the team Mechanical Advantage. And it allows you to log a lot of information about your robot, but it requires you to log enough information that you can actually replay basically all the code going on while your robot is running in a match after the match. So it's basically complete replayability of everything happening on your robot, which allows you to have access to any information that you could possibly want from the robot that possibly could have been gotten. So basically a guarantee of no case where it's like, oh, I wish I had logged that value during the match. You're never going to run into an issue like that. But it does come with a lot of structural requirements and a lot of constraints on your code style. So that is one thing about that. It's more of a framework. Complicated, but very, very powerful. Monolog is a lot less complicated. It basically does the same thing as network tables and a data log manager implemented well, but way easier. But it still does have some requirements on the structure of your program, and basically it uses the class structure to generate where it logs information. Doglog is the least complicated. It's incredibly simple, as you see, so we'll use it today. It has almost no constraints for how you use it. And you easily install it from a vendor dependency. So we'll demonstrate that in the lab section, but it's pretty easy. You just look up like doglog FRC, and then it should have an installation page, which gives you the vendor dependency link. So to set up logging, usually you would put this in your robot container. What you're going to do is public void configure logging. We just have this extracted into a method. You could put this in the constructor, for example, but we like extracting it for clarity. And you set your options. Usually the only option you're going to need to set to be true is network tables publish true. And this enables telemetry. So you can actively live see in network tables all the stuff you're logging. And you just use this new doglogs option class to do that, and this set options method. So pretty much just this code. And then if you want to log your power distribution hub data, which includes stuff about like voltage and current draw on like different ports and stuff, you can log that by just typing this. You need to import power distribution, but that's basically all. That's all the logging setup required. And then to actually log, all you need to do is call doglog.log, and then whatever key you want to use for logging. So it's kind of like a file path. All your logs will go under this path, basically. And then you just pass whatever value you want, right? So right now, this is probably a double. So it'll just log a double there. And this will also log a double. It's literally this simple. If you want to like log a pose or something more complicated, like an object, a lot of the built-in WPIlib classes have something called protobuf and or struct support. And if your class has protobuf or struct support, which is basically all the WPIlib built-in classes, you can also just log that directly. So that means you could also log like a pose or a rotation, a translation, a ton of things. Super simple like this. And that's all there is to doglog. So Advantage Scope, right? Not to be confused with Advantage Kit. Advantage Scope is a log viewer and a telemetry viewer. So Advantage Scope is actually included in the built-in game tools you get when you install WPIlib. So theoretically, most of you should have it on your computer. But basically, it's an app that you can use to view logs, and we'll demonstrate that in the lab section coming up quick. here's some instructions for how to use Advantage Scope. Basically, if you're connecting to a robot, you just make sure your team number is set to the right number, and then you choose to connect to a robot. If you're connecting to a simulation, you just do File Connect to Simulator. And then it has a very nice UI with kind of all your fields from network tables on the left side. I'm not sure if this is the left from your guys' perspective, but it's my left. And then you just drag them into the viewer, and it has lots of view display options, which we'll see in the lab. So for simulating, there's also a lot of options. Advantage Kit has a simulation option kind of built in. Again, very complicated, but also very powerful. You can use the built-in sim classes. Now, this is something that I would honestly recommend a bit against, except for in very certain cases. I wouldn't use this by itself for your simulation solution. Phoenix 6, right? So like CTRE products have vendor libraries that allow for simulation, but Rev, for example, does not really have much, if any, simulation support. So you can kind of use built-in sim classes. They're odd to work with and very inconsistent. So dependency injection is basically where instead of having a motor in your subsystem directly, you have a class that is either a real motor or a simulated motor. And it basically has an interface, which if you know Java object oriented programming, this interface would have pretty much a set speed method or any other methods you really need. And when you create your class, if it's a simulation, you would pass in a fake motor. And if it's actual reality, you would pass in the real motor. But dependency injection is pretty much the word you would use for this. It's a lot like the Advantage Kit solution, but it's a lot more flexible. We're not going to go over this much. I would recommend this if you're really serious about simulation, though. It's a very good long-term solution. And then today we're just going to be manually doing it, which is basically using if statements to tell if you're in a simulation. And if you are in a simulation, you like manually update the position of motor encoders and manually update their speeds instead of allowing the actual motor to do it because there is no motor. That's what we're going to be doing today. So to simulate setting speeds, what I would do is we'll create a few new fields, right? So M left sim speed, right? And that's kind of just going to record what was the last value we set our motors to go at. So anytime you set your drive speeds, if you're in a simulation, we're also going to set those to kind of keep track of it. Because for revlib, at least, if you do M left leader motor dot set and then your percent, it doesn't actually change what value you'll get when you do dot get if you're in simulation. So you need to record it separately. Then for simulating speed, right, we want our motors to change position if they're going at a certain speed. So we see what speed our motor would be going at. And this motor class is using something called a DC motor class, which we'll demonstrate in the lab. But just know if you do DC motor, it's a static class, and then dot get, you can type in pretty much any motor name, and it'll give you a class that you can then call dot get speed on. Now, torque, we're going to use 0 for this example, which is completely unrealistic given a realistic scenario where motors always have some amount of torque on them. And then we're just going to put in the percent output we have, and this should give us a estimated speed if the motor had no torque on it. And then we're also multiplying by 0.02 because that is how long a single periodic cycle lasts. Then we convert from radians to rotations because the encoder values for rev are measured in rotations. If you're simulating like a CTRE device, you would have to use a different conversion here. But pretty much what this does is if we set our speed to 1, our encoder positions, our simulated encoder positions here, are going to continuously increase as long as our speed is set to 1. Now for getting speed, if we're in simulation, we'll just return the simulated speed that we got. Otherwise, we will return our motor's actual velocity, right? And for getting position of a encoder, we're going to check, are we in a simulation? If we are, we'll return our simulated encoder value. And if we're not, we'll return our actual encoder value. So now it's time for the lab. Basically, we're going to log positions and speeds, specifically on our tank robot we have over here. The steps to do that is add logging, and then pretty important, view in advantage scope. That way we can actually read our logs and our telemetry. And then second, we're going to make a simulation for driving, where basically we add simulation for all the motors. And since from our last class, we already have our odometry and stuff created, this should basically allow us to drive around in our simulation. And we'll demonstrate that. So moving back to our code. Last time we were working on autos, and we didn't quite get the path planner autos working. One of the issues we found for that, basically there were two main issues. I forgot to multiply by math.pi here when calculating the wheel circumference of our robot wheels. I just decided that I guess circumference is equal to diameter, but you do need to multiply by math.pi there if you're calculating from your wheel diameter. So that's one mistake that caused some issues with our odometry distance not being right. And then one big mistake that was very, very hard to spot that I would like to point out is this right here. So in some spots in the code, I used mgyro.getRotation2d, and at other spots, I used mgyro.getAngle, which, as you can see, gives it in degrees, right? And so I thought that you could do rotation 2d dot from degrees like this and get the same thing as this. It turns out one of these actually rotates counterclockwise and the other one rotates clockwise. So they give you basically the negative of each other. You should probably just use get rotation 2d. I would not recommend using the dot get angle. But basically, one of those was being used in one spot in the code. The other is being used in a different spot in the code. So every time we reset our angle, it wasn't actually resetting the angle. It was setting it to the negative of what it was supposed to be. And then it was just messing stuff up. So that was pretty much the main two issues there. We actually figured those out using telemetry because we were able to look and see, okay, it thinks it's here. And when we're resetting its position, it's not actually resetting it. But I deleted that telemetry, so we're able to add it back in now. So we're going to start by making sure we have dog log. To do that, we're going to head in here and look up dog log. And you can actually do doglog.dev, should work. Very nice and concise URL name. And I'll post that in the chat. Actually, I'll just post the vendor dev in the chat, but you get started. And then it's just right here, literally the first thing. Copy it. It should be in the chat as well. And then what you're going to want to do is go up here, manage vendor libraries, install new libraries online, paste. And I get a library already installed warning. You should not get this, assuming you haven't already installed doglog. Now you're going to want to go into robot container, and here we already have it set up. So basically, doglog.setOptions, new doglog options with ntpublish true. So hopefully you guys are able to see that. Right here. Theoretically, if you're in a actual FRC match, you might want to turn network table publishing off. One disadvantage of that is if you're logging stuff to your driver station using this, it'll stop logging the stuff to your driver station. So you'd need to manually do that again. But it does save on some bandwidth, which you might want to save in the case of a match scenario where maybe the FMS can't handle all the data you're trying to send. One way to have the same code for both actual competition and at practice, but have it react differently in an actual competition is using driver station dot is FMS attached. And basically, this is going to return true if you're at a comp. So Boolean is at comp. And it's going to return false if you're either like directly attached to your robot via Wi-Fi or via like an Ethernet cable. So for example, we could do network table publish not is at comp. And then we'll only publish our network table data if we're not at a comp. Otherwise, we'll save it for the data logs that we can review after a match. So you'd use that if you're using network tables primarily for debugging. We're just going to leave this as true to not cause any issues. That's almost all you need. If you really want to log your PDH stuff, your power distribution hub, you just do log and then, or set PDH, and then new power distribution hub, just like that. And for the most part, that should cover your power distribution. So this is pretty much all the setup you need for Doglog. Any questions? I'll take that as a no, so we're going to move on to the drive subsystem. For logging, usually you want to do it every single cycle that your robot has. So in our case, every period. Every 0.02 seconds. And just to make it a bit more clear that what we're doing is logging, we're going to make a separate log method. And let's call this log info. Right? And we're going to call this every period. And this helps keep your periodic method looking clean so you know exactly what's being called every period. And it helps make sure you're only really doing logging stuff in log info. And it kind of reminds you to keep it all together. But we're going to do doglog.log. And now we can kind of decide what we actually want to log. So I think for this class that we have set up right here, some stuff that would make sense to log is the speed that our left wheel is going at, the speed our right wheel is going at, the positions they're at, and also the pose that our robot is at, and maybe the gyro. I think those would be the things that would make the most sense to log for this class. So the first thing you need to do is you need to choose your path. I would recommend basically doing your drive, the subsystem that you're logging for. So in our case, drive subsystem. Or maybe if you have info you really want to log for a specific command, you could do the name of the command, like maybe drive command. But we're going to do drive subsystem. And this is also completely up to you. There's no truly correct way of doing it. It's just whatever makes the most sense. So drive subsystem, and then we're going to want to do speeds. And we can do left first. So we're going to want to log our left speed. So this is going to be our right speed, actually. We're going to want our left speed. So I'll just copy that from up there, paste it, and that should be the left speed. And then we're just going to do the same thing for the right speed. So type in doglog.log / drive subsystem / speeds / right and it'll log that double value. We're going to want to log our encoder positions. So dog log, then /drive subsystem /encoders /left, and we can do motor, or actually we have it set up here already. Get left encoder position, get right encoder position. So get left encoder position. And then get right encoder position. And that pretty simply allows us to log our encoder positions. Then finally, and this is one of the benefits of using something like dog log as opposed to network tables, dog log can very easily, almost seamlessly, log information like pose. So we could do drive subsystem and pose, right? And then we can just do get pose. And it can just log it that simply. If you use network tables, you'd probably need to make a method to individually log the X, Y, and Z values for your pose as a list, which is just less convenient than this, and it doesn't send as much information to network tables about the fact that like this is a pose. So then we're also going to log our gyro rotation. So and then gyro, and then get gyro. And then that should give us a rotation 2D. Log, pose, and rotation. Now, theoretically, the rotation from our pose and the rotation from our gyro should be pretty similar. Or at least they should go together, but the gyro will probably be offset by a certain amount. So it is useful to log them both. Now, if we try building our robot code just to make sure everything works, hopefully it works, we will be ready to deploy to a robot in that case, and should be able to view our logging information in that case. So if you have any questions, now's a good time to ask that for them while we get this set up to deploy. So it's executing task, Gradle W build. Hopefully it goes ahead with that and succeeds in building. There really aren't that many changes to the code, so I don't really know what's taking it so long, but oh well. So it's starting the Gradle daemon right now, which is taking a lot of time, I guess. So perfect time to ask questions, but After this, after we deploy our code, we're going to be working on viewing it in Advantage Scope. Now, Advantage Scope, hopefully you should just be able to look up like Advantage Scope. And as you can see, yes, for me, it was installed with WPILib, right? So you'll see that WPILib in parentheses 2024. You can also install it from the Windows App Store, and you can download it online. You should also be able to install on the Mac App Store, I believe. But if you download WPILib, just searching Advantage Scope should bring it up for you. I'm going to use this one, and I'll only open it once we're done building because I don't want to bog down the computer any more than it already is. Let me make sure I've got all my like windows for stuff closed. Maybe this is causing an issue. Okay, there we go. Okay, so sorry that took 3 minutes, but it did successfully build. So now we can deploy that robot code to our robot. We're hardwired here, but if you're at this step, you would connect via Wi-Fi to your robot. And also something I would advise doing, usually if you've installed a new vendor dependency, is building well connected to Wi-Fi before deploying to your robot. Because often what will happen is you'll try deploying to your robot and then it'll be like, can't find vendor dependency. Because when you build that first time, it'll often download a lot of files. So we successfully deployed. Here's we're getting some interesting stuff there, but we're just going to ignore it. Probably means that the logging is succeeding. So we're going to open our Advantage Scope. And we're going to first show preferences. And Windows, it's going to be here, show preferences. And you're going to want to change your RoboRio address to 10 dot and then your team number with like a period in the middle. If your team number was 3 digits, it would be like that. If it was 2 digits, it would be like that. If it was 1 digit, it would be like that, right? But we are 4 digits. And if you're 5 digits, it'll be like that. So, to my knowledge. So, boom. Everything else by default should be good. Then you're going to want to do File, Connect to Robot. It appears we're not properly connecting. This may be because we're actually hardwired to the robot, which is unfortunate. I guess it would have a different IP address over the USB-B. So yeah, unfortunately, we are not getting a connection here. So we're going to need to show this on a computer that can actually connect to the robot. So sorry for this screen on screen stuff again. Hopefully you can kind of see the computer. But right here, this is connected to the robot. We're connected via the driver station. If we open up Advantage Scope, let's see if I can turn the brightness down on this. Basically, we have Advantage Scope here, and it's the same layout you're going to see. You want to do, as I said before, File, Connect to Robot. This one actually has a different team number set right now, so we're going to need to change that again. 25.39 for us at least. Check. File, Connect to Robot. And hopefully it should work. There we go. So we successfully connected, and you guys might not be able to see it, but right now, here, we have a bunch of numbers with timestamps on them. And on the left here, we have a bunch of information being logged. So if I click on a robot, we have 3 drop downs. We have dog log, which is basically just logging some information about dog log's status right now. Are you kind of able to see that or no? So basically stuff like the options that are currently set, not super useful, but I guess it's good for diagnostics. You have the stuff we were logging, so drive subsystem, and then if we go under speeds, we can see left. We're currently missing everything else though, which is a little discouraging. We also have system stats, which includes all that information about the what are they called? The PDH. But yeah. If we enable
only present this, stop presenting that screen just to make that bigger.
1 second, sorry. So if we were to drive the robot forward, or actually, if you press this little red arrow, it brings you back up to the front of all your data. We drive the robot forward or around it all. It's not moving right now. 1 second. Are we connected to our joysticks? It appears we're connected. It also appears that whatever we did when we deployed to the robot prevented it from moving. So we're having a slight technical issue at the moment. So let's make sure that gets fixed. So right now we're just trying to redeploy without the logging, see if that allows the robot to drive at least. But so redeploying without the logging seems to have fixed the issue, at least temporarily. So I'm going to redeploy, but with logging again and see if it just needed like a redeploy. I think that might have been the culprit. So it didn't run that time. It appears I'm getting some errors in relationship to logging the PDH. So I'm going to try disabling logging that. Previously that did work, but this is kind of an old RoboRio, so it might not be able to be publishing that much data, which is a possibility. So yeah, both the radio and RoboRio are kind of old, so we could be having some issues in regards to that. That's one of the reasons you might not want to log your PDH data. It can increase the bandwidth quite a bit, but
That's a heat. It's not a PDH, so it's probably gonna vibrate.
okay. Alternate issue possibility is that this does not actually have a PDH, but instead has a PDP, in which case we might be getting errors from that. So right now it appears we have no errors. So we enable. Okay, no issues there. So basically, some robots will have a PDH, some robots will not. Only log the PDH if it has a PDH is what we've determined here. So
We don't send data.
okay, PDHs will send data. PDPs do not send data. Our main robot does have one that sends data. This one does not. So unfortunately, that caused our issue. So if you have a PDH, you can log it. If you don't, I guess it'll cause issues. So switching our view back to our Jenki network table setup and stopping to screen share here because we want to maximize this view. So on the left, we basically have a bunch of fields that you can choose from. We're going to drop down here and we can finally see all our fields. So we have encoders, the left and right positions of them. We have our speeds. Right now, they're both basically 0. We have the pose the robot thinks it's at, and we have our gyro. So up here in this corner, there's a plus button, and you can use that to add new views, and there's a ton of them. The two important ones, most important ones I'd say, are line graph and odometry. So odometry you can drag pose out into. Basically, you click on it, hold, and you drag it into poses, and it'll show up there. And right now it's showing up as a ghost in our bottom left corner. I'm going to change that to robot. And let me make this full screen so it's more visible. Right there is our right there in the bottom corner is our robot. And if I enable and drive forwards, as you can see, our robot is driving. We have it on blocks right now, so it doesn't like crash into a wall. Also because we need it to be plugged in to the computer at the moment. But if you drive it, its position does update, as you can see. And also if we turn, it actually doesn't turn, and that is specifically because it's not physically rotating and we're getting the rotation from the gyroscope. If we were to, and you know what, we can. If we were to rotate it, we're taking off the blocks right now, so we can actually properly drive it. We drive forwards a little bit, you see it does that, but then if we rotate, it uses the gyro to get that rotation. And that's because using the gyro is a bit more accurate than using solely wheel odometry for that. So that allows us to drive the robot around in real life and see its location on the screen. And as you can see, if we transition over to line graph and plot this, our left position and our right position, they are both changing, right? So if we drive backwards, they go down. If we drive forwards, they go up. And if we turn, one of them goes up, one of them goes down, right? That kind of allows us to get that information. Any questions right now? I will take that as a no. So additionally, we have the gyro. We can log that on this right axis. Basically, that's just how much it's been rotating. That's the yellow value, if that's showing up very well on the screen. You have two axes, pretty much. You have your left axis and your right axis. So if you have stuff that's different units that you want to display differently, you can drag it either to the right side or the left side to get different views for that. Also, if you're logging something that's either like true or false, you can put that in discrete fields. So for example, we have FMS info, and one of those things is Red Alliance. We've been the Red Alliance this whole time. So down here we have it as true. It's this purple bar, solid purple. If we quickly disable, go into this, and then change our station from red to, let's say, blue, that is going to change to false. Now, I'm zooming in a little here. You can zoom in by scrolling. But as you can see, it goes from dark purple to a light purple, meaning it's now false. And then we can enable again. In odometry, this little bar at the top, if it's green, you're enabled. If it's red, you're not enabled. And also note, you can pause or press that button to stop moving. And you can drag your cursor along your history to see where your robot was at different times and basically see data in the past. So Advantage Scope automatically records your telemetry over time, which is very useful. One other thing that we can display here is the different speeds. So left and right speed, if we just pop those in, those are going to be single units pretty much. So let's get rid of these so they can actually show up on their axes. But as we scroll out, we'll see that they do in fact have values, but they kind of return back to 0. So if we're driving straight, they're basically the same. If we're turning, they're opposites. And if we're doing a combination, they're a combination of being together and opposites. So I guess just like completely unrelated in that case. Also, as you hover through, you can see your values change there. So we're going to jump into simulation, and this, theoretically, we won't need the robot anymore, and should be completely visible on this one computer screen. So sorry for that camera view, but we should not need it anymore. So hopefully you guys can see my screen again. Okay, I'm getting a thumbs up. You can see my screen. We're going to go back into our drive subsystem because we're going to want to add some simulation information to allow simulating our drivetrain. In this case, since we only really have the left side and right side of our drivetrain you need to simulate, since it's a relatively simple subsystem, we can just add the velocity of our left and right sides as fields and then the encoder values as fields. So if we do private, double, and then m, left, sim speed, and we can just set that to 0 by default. Private, double, m, right, sim speed, 0. Private, double, m, left, sim, pose, or I guess encoder value. And then private, double, m, right, sim, encoder value equals 0. So those should all give you warnings because right now they're unused, but we will make them used. So the real only position where we're going to be setting one of those is down here in this set speeds method that we already have. So we're going to do m left sim speed equals, and just the left speeds, and m right sim speed equals right speeds. Now, this technically doesn't need to be put in a is simulation bracket because if it's not a simulation, this just won't do anything pretty much. We're just like setting variables that we're not going to use. But it's probably a good practice to put it in a simulation if statement. So you can do robot dot is simulation. And robot dot is real is literally just the opposite of is simulation. Sorry, this is a little laggy. Okay, there we go. Robot dot is simulation. Success. Let me make sure I have my Advantage scope closed for now. That can add some lag. So now any of our commands that are setting speeds should function properly with the simulation. We're also going to want to go down here and add a new simulation periodic method. And this only gets called during simulation. So simulation periodic. And what we're going to want to do with this is we're going to want to update our encoder values based on our speed. So right sim encoder value and plus equals m right sim speed. Now, there's a few things wrong with this right now. So our right sim speed is not actually a speed. It's a percent output that we're setting, right? So this is the percent output on the motor, which is in, technically it's unitless, but for our purposes, it's kind of like voltage. Basically, this is voltage, and we're just adding it to our right sim encoder value, which is measured in rotations. And voltage is not rotations. So we need a few steps to get from this to actually something correct. So let's say, basically, we need to convert this first to the actual speed that that wheel is going to be rotating at. And then we need to convert that rotation speed to a change in rotation based on the amount of time elapsed. So for that first step, we're going to use the DC motor class. And usually you would create this at the top of your file. I'm going to create it here for now, this new field, just so we can see it in very close relation to this. But final, and then DC motor. And we're going to call this sim motor equals DC motor dot get, and then you would use whatever motor you're using. So we are using a Neo here. So we're going to do get Neo, and then it's going to ask you for a number of motors. We're going to say 2 because we have 2 motors on each side of our robot. And then you have a few options. You could do dot with reduction. That's actually really the only option at the moment, but we're not going to put a reduction on this just yet, because really we're getting our raw encoder values and then we're doing some math on them everywhere we're using like get encoder.get velocity, right? Then we do a ton of math on it afterwards. We're not actually getting it after the gearbox. So we're just going to leave it as is. So what you can do is you can do sim motor dot get speed, and we're going to put in 0 for our torque. Basically, we're assuming that the robot has like nothing pushing against it, right? Which in reality is not true. You always have the torque created by trying to accelerate, right? Acceleration requires force, and when you put force on a wheel, that generates torque. So there's going to be some torque there. For simulation purposes, right, we don't want to go super heavy with the physics for this. We just kind of want the robot to move when we move our joystick. So no torque, and then our percent output. And we're going to multiply this by 12 because this is in units from 0 to 1. Our voltage we're going to be applying to our robot is 12 volts, ideally. And as we can see from this method, it takes the input in volts. So now we have the speed in radians per second of the motor. At least I'm assuming radians per second. Usually the WPI Lib math classes will return stuff in radians, if not specified. That also makes sense in this case, as everything it's asking for is in the metric system, and radians are generally the default for the metric system. So sim motor dot get speed, and we have radians per second. So we're going to use units dot radians per second to, and we could do rotations per minute, but what might actually make more sense is to do just radians to rotations. This is already in radians per second. So if you do radians to rotations, it'll get an output in rotations per second. So now we have our value in rotations per second, but we're still adding it to something in rotations. So we need to multiply by the amount of seconds, in this case, 0.02. So this right here will properly update our right sim encoder value based on the speed that we have our motor set to. So let me break this out into a few lines so it's a little easier to see and read. So you want to take this and you want to copy it probably and just do the same thing for your left encoder value. And now we should be updating our encoder values. So far we have a way to set those if we're in simulation, and also if we're in simulation, we'll constantly be updating them. So I'll leave this on screen for a few seconds. Does anyone have any questions right now? I will take that as a no. So we will continue. Now, at a lot of spots, we're calling methods like this, like get left encoder position, get right encoder position. It's good we already have these separated out, because what we need to do is we kind of need to replace this with a way of accessing these sim values. So here we're going to go to get left encoder position, and we're just going to start with this because we already have it separated. If robot.isSimulation, then we're going to return our left sim encoder value. And we're going to do the same for the right one as well. So if it's simulation, we're going to return our right sim encoder value. And basically, this just kind of takes anywhere we're getting that encoder position, and if it's a simulation, we return the simulated value, not the real one, because the real one is not going to have changed one bit. Now, something else we're also going to want to do is make sure we include that division at the end, because this is in encoder rotations. This is also in encoder rotations. So we still need to apply this little division. Now, right here, we're calling .getEncoder.getVelocity. So we want to be able to get the velocity in simulation 2. Right now, this isn't going to cut it. So we need to make 2 new methods for getting the velocity. And while we're at it, we may as well extract this part too, because clearly we want to get this in speeds. Actually, I think somewhere we might be logging this differently, so we're not going to extract the whole thing. We're just going to extract this. So public, then double, get left encoder velocity. So if robot is simulation, can do stuff, and we're going to return in there eventually, but we're going to write the base case first, the case where it's not a simulation. And that is just going to be this right here. And then we're going to put get left encoder position, get left encoder velocity right there. And this is equivalent to what it was at the moment. Now, another way to do that, if you don't want to manually write that all out, is you can left click on that. And then if you press, I think this, extract interface might be correct. Okay, that is not correct. Often you'll have an option to kind of just extract that code into, there we go, extract to method. So extract to method would be the button, but it'll extract it to a method right there. And we're going to call this one get right encoder velocity. And that pretty much does the same thing we just did, but it has the computer do it for you. It has your code editor do it for you. And in this case, it's not too bad. But if you had some code you really wanted to refactor and kind of break up into methods, this is a lot faster of a way of doing it. So we're going to take this same robot is simulation thing and copy it down here. Now, if it is a simulation, right, we're going to want to return our sim speed. But it's important to remember this is still our percent output, not our actual velocity. So we're going to scroll all the way down here to the last place we did this. This is our velocity in rotations per second. This is our velocity in radians per second. So we're going to copy the radians per second and run all the way up here and paste it in. Now, one thing, this returns RPM. This is radians per second. We're going to use that method we initially glossed over. Radians to second per 2 rotations per minute. And this finally should return pretty much identical to this, but simulated. So if we copy this, run up here, and paste it in, and then just make sure to change that right sim speed to left sim speed. Our simulation should have the left encoder velocities dealt with. So now we just need to do a quick scan through our code and make sure that everywhere we are trying to get the encoder position, unless it's in one of these methods that we have designated for that, we need to make sure we're using the get encoder position methods or the get encoder velocity methods. Otherwise, we will run into issues. So I'm just doing a quick scan right now, making sure we're not using that anywhere we shouldn't be. Here's an example of where we shouldn't be. Here it actually appears, this is something I didn't know that VS Code would do, but we were using the same pattern we were earlier, and when we extracted it into a method using refactoring, it also refactored it down here, even though we didn't specify to refactor it down here. But we're going to do get left encoder velocity there. So now this should go based off of sim, this should go based off of sim, and these two should go based off of sim. This is also going based off of sim, and this is for simulation only, so it's always going based off of sim. So now that everything is going off of sim, we should be able to simulate our robot code. And the way you do that is you go up to the W. It's a lot like deploying, but you type sim, and it should be one of the options. Now, after your build succeeds, you should get this little pop-up at the top. And it's going to have two checkboxes. It's going to be like sim GUI and use real driver station. And if you press neither of those, you're not going to get much that's super useful. So I'd recommend pressing at least one. I usually just go with sim GUI, which is what we're going to do for now. So I'm going to press OK. And also, if you click off of that instead of choosing one of the options, that'll like disappear and then nothing will happen. So if nothing happens after you simulated, you might have clicked on something that wasn't that, and then it probably just canceled. So it's going to start this debug shell for you. It's going to type all this random stuff. And then shortly, you should have a window pop up. Here we go. This is our window. And it's your robot simulation. So this will probably have some classes. Like here we have all the Spark Maxes and the Navex we have. And these are not super functional, honestly. They don't really do a lot. Navex doesn't really support simulation properly, so you can't actually use them very well. Down here, you're going to see a lot of stuff. You have your network tables, connection info. It'll tell you who's connected to it. Right now, we have no one connected to it. We do have some publishers, though, right? Like Doglog, pretty much anything where any data we're publishing shows up there. Subscribers, those will show up. We have some stuff for Path Planner there. And then clients, no clients yet. Network tables here. It's another way of viewing your network tables data. So we can go into robot, drive subsystem, encoders, and we can see all our encoders. And they're all perfectly at 0. How lovely. This is a way of assigning your keyboard to control your robot. And that's what we're going to do for now. So you can drag keyboard 0 to joystick 0, keyboard 1 to joystick 1, and keyboard 0, your axes are controlled by W, A, S, and D. So axis 1 is W and S. Axis 0 is A and D. And then axis 2 is Q and E, or it's E and R, not Q and E. And then for these 4 little buttons at the bottom, that's Z, X, C, and V. So they function as your button 0, 1, or I guess button 1, 2, 3, and 4. And then for keyboard, or I guess keyboard 1, it's basically I, J, K, and L as your joysticks. And then M, comma, period, and slash on an American keyboard. So those, what? 1 second. Our screencast appears to have disconnected from our TV. So. So anyway, yeah, just drag keyboard 1 to joystick 0, keyboard 0 to joystick 0, keyboard 1 to joystick 1. You can also actually plug in your joysticks if you want. I might actually do that to demonstrate that is a possibility. But actually, we're kind of almost out of plug-in spots at least. Bye. Plug that in. They may or may not show up. There we have them show up. So I'm just going to drag T1 there to make this easier for me to control. Drag that one there, and then our Logitech joystick there. These actually need to be swapped. So okay, so now my joysticks are properly connected and our gamepad is connected. And if I press buttons on them, they show up down there. So you can connect the simulation that way. Now, up here in robot status, you can change whether your robot is disconnected. Right now it's disconnected, disabled, in autonomous mode, teleoperated, or in test mode. And you can also change whether the FMS is attached, what alliance you're on, blue versus red, what station you're in, and also the match time if you're in auto or teleop. A lot of useful stuff. We're going to switch to disabled real quick. And we're going to pull up advantage scope. When advantage scope opens, you should be able to press on file and then connect to simulator. You shouldn't need to input your team number for any of this. Now we can go down to drive subsystem and then drag out pose. And we see it right there in the corner, and we're going to want to change that from ghost to robot. Now, if we enable IntelliOp, and I drive forwards, as you can see, the robot drives forward, and I am, in fact, moving the joystick forwards. And if we turn, we're going to find we're not turning. Now, why is that? Again, it's because the gyro, right? Gyro always causes issues. Specifically, the way we're doing our odometry right now, it uses the gyro to generate the angle that it thinks the robot's driving at. So no matter how much we tell it the wheels are turning, as long as the gyro isn't changing, you're not going to get any response. But we do still have that first step of being able to drive forwards and backwards down. Our joystick inputs controlling an imaginary robot, right? First step complete. So to stop the simulation, you can press that red button there. Now, getting this gyro step working is kind of annoying, to say the least. Pretty much what you need to do is you need to manually update your position using odometry dot reset position. And you basically need to take your current position, add the amount that you should have rotated since last time, and then pass the current gyro values. Alternatively, you can record your gyro value separately, like we did for all this other stuff, and make a sim gyro. I honestly think that might actually be the easier solution in this case, due to the way we already have everything set up. So right here, we're calling mgyro.getRotation2d. Let's extract this. So refactor, extract to method, and we're going to call this get gyro rotation 2d. So now any call to this is actually going to route to here. So we're going to do an if robot.is simulation return m sim gyro rotation. Now this isn't real yet, so we're going to need to create it up at the top. Right by our other sim values. So private rotation 2D m sim gyro rotation. Sim. And we're also going to want to set this one to just be 0 initially. So you can do that by doing new rotation 2D, which defaults to 0. If we scroll all the way down here, all the way at the bottom, boom, simulation periodic. What we're going to need to do is update that gyro simulated angle based on our chassis speeds, pretty much. We already have a way to get chassis speeds because we had them for creating autos, but get chassis speeds. This method here is how you would do that if you weren't here for the last class and didn't have a way to get chassis speeds. So I'll leave that up on screen for a second or two. But we're going to go down here and we're going to make chassis speeds, current speeds equals get chassis speeds. And from current speeds, we can get a few things. We can get our VX speeds, our VY speeds, and we can also get the speed we're turning at. We're going to take that. We're going to multiply it by 0.02. So now we have how many radians per second are we changing? We're going to want to make a new rotation 2D from that. So rotation 2D from radians. For rotation 2Ds especially, I would always recommend using the rotation 2D dot from and then whatever unit you're using. The default constructor uses radians, but I think this is a lot clearer. So we now have how much we're rotating, and we need to add that to our current rotation. So we're going to do m sim gyro rotation equals, and then m sim gyro rotation dot plus this amount right here. So this center value is pretty much how much did we rotate in the last 0.02 seconds according to our wheels. And then we're saying, okay, we're going to add to our current gyro rotation that amount. So this is the most, I guess, similar way to the way we did our encoder values of doing gyro simulation. Now, hopefully, when we simulate the robot, we should be able to turn as well. Fingers crossed. So we have our robot simulation again, our joysticks. One is not connected for some reason. Okay, there we go. Second joystick connected. We're going to teleop enable. All right, switch over to this. As we can see, we're enabled. I drive forwards, I drive, I turn, and I'm actually turning. All right. Now, it is worth note, if I turn this joystick at like 50% or like 10%, the robot's turning very fast. And that is actually accurate speeds to if you were turning that fast. The robot is capable of turning very fast. Usually you would set like a percent multiplier on your turning speed so you don't turn that fast. The only difference between this fake robot and the real robot is the real robot has inertia. So when you move the joystick to the left real quick, it takes time for the robot to speed up. And just the way the physics works out, that inertia happens to slow down the angular acceleration of the robot a lot more than the linear acceleration, at least in comparison. So I can drive around as much as I want. I can make little curves, figure eights, and basically just simulate driving the robot around. I can also press one of our buttons, I think, or maybe it's that one there. I press the button that switches us back into tank drive. And as you can see right now, it kind of looks like I'm only driving one side of the robot and the other side's sticking still. And I can also do the same with the left. So now I'm in old-fashioned differential drive instead of arcade drive. And if I press the button that is supposed to make the robot spin, or I guess that button, I think I remapped that to reset the position of the robot in the last, when I was doing some debugging. But alternatively, that button could spin the robot around. It probably would. So to reset the position of the robot, you just call the m.reset odometry, and then you use the current pose. So I have that button bound. It sets us back there. And I can drive around as much as I want. So very cool. That's pretty much it. Oh, one thing pointed out, this 3D field tab, this is actually really cool. Just if we're showing off stuff that Advantage Scope can do. You have your line graph, you have odometry. If you do 3D field, it might take a second to load. This laptop is probably on its brink of blowing up due to heat, but it is a 3D field, which is very, very cool. You can drag your pose onto it, and you can also do a 3D pose in this. 3D pose isn't just X, Y, and rotation, but it's X, Y, and Z, so it has a height, and also it has a full 3D rotation. So I know some teams have very good odometry and gyro and April tag combinations for basically keeping track of their pose, and they've like tipped over in matches, and you can physically see their robot tip over in their logs. It's very cool. But right now we just have our robot there. And if I drive forwards, it drives around. So that's pretty cool. If you're interested in stuff like this, if you're really interested in Advantage Scope, there's options to upload models of your robot from CAD. If you have CAD, you can change the model to pretty much anything you like. Like this would probably be more accurate to what our robot actually looks like. And also you are able to change your view a bit. So if you left click, right now it's orbit field. You can orbit the robot So if the robot moves, you follow it, kind of keep its perspective. So if you want like an on-robot simulation perspective, that's one way to get it. My left click would work. I'd be able to demonstrate some other options. Unfortunately, it's not appearing to work super well at the moment. Okay, there we go. You can choose different driver stations to look from. So let's say we're in the blue driver station, right? This is what that would look like, right? And we're driving our robot around, driving off the field, it appears. But we can see our robot over there, and you can kind of get a grasp on how it would feel to control a robot from a certain driver station. This isn't working super well because it has significant delay because this computer's kind of dying, but that's something pretty cool you can do. 3D field, lots of different perspectives you can get there. You can also, something else really cool you can do with the 3D field that definitely not going to go into how you fully get that set up, but you can not only just upload a 3D model of your robot's CAD, but you can link the mechanisms on that to fields you're publishing in network tables, and you can have like an animated model of your robot displayed. Otherwise, some very slightly useful fields. Joysticks, if you're logging some joystick data, we're not right now. There is an option to log joystick data. You can display it in joysticks, so you can look back over your match and see, okay, what buttons were being pressed. That can help you determine if things were like operator error versus a programming issue or a mechanical issue. There's this swerve view, which we'll use a bit next time when we go into swerve. And there's plenty of other views. This video view is actually very useful if you have a log from an official match, which just, you can open a log file by going to File and then Open, and then you can choose logs from like JavaBot logs there. You can actually download logs. From your robot. It can't find a RoboRio there because I'm not connected to the robot right now because we're in simulation. But if you use video, it can actually connect to the Blue Alliance, download the video, synchronize it with your match log, and then you can see your logs compared to the video of the match automatically. So that's also very cool. Otherwise, that's basically all for the day. We completed the lab. So thank you for attending. If you're still here, come back Wednesday for a demo on how we at least do swerve with our CTRE trifaces. So